So I'll be continuing on some of the material covered Thursday. On Thursday I was talking a lot about navigational techniques for a robot, and I very briefly touched on the inertial measurement sensor. So your lab today is entirely to do with that sensor, and you'll play around with it, see how it behaves, and then learn about how you can use it in your robot for detecting angle and movement. Before I get started, some quick announcements. These are things I had somewhat alluded to a while back, but I never gave you a hard date. I guess because of midterms around your first progress report, that's being pushed back to the 30th of June, so that's a week and a bit. Because I'm away next weekend, so if you email me, I might be slow. So I wanted to give you a bit more time in case there's questions with that. I'll discuss more of the format of it on Thursday, June 18th, so this Thursday. The final report, there was also, I guess, a final rate on that same day. So it was originally due, I think, the Monday. It's just pushed back to the Thursday. That's kind of the end of the class, so that's the last day they can be submitted. These don't, I had mentioned a while back, these don't have the same extension option that the rest of your stuff does. You have that 1 week that you can use once. So these you have to submit them, and there'll be some time, probably 4 p.m. or whatever, on that day. But I'll update the schedule with that and send an announcement. I just wanted you to be aware of that. I also mentioned a while back there was going to be this idea of open source projects, which is to say, basically if you design a section of the robot and post it for other people to use, in order to reward you for sort of helping everyone, you'll receive a few extra points on the final competition day. I'm going to post those tomorrow morning as what the full rules are, but basically there's going to be 5, and I may add a 6 possible projects. So for example, building a code that interfaces to the motor driver, and you nicely document it such that someone can use it easily. And the same thing for the compassing, the inertial nav stuff. So this is what we'll be doing in the lab. If you extend it a little, package it nicely, document it for someone to use. There's the dead reckoning for the motor. So this is where we have sensor disks on the motor to detect how far your robot's traveled. And this also includes design of the 3D printed parts that go on the encoder shafts. So there's a bit in that one. A range finding driver, so interfacing to the rangefinder system, and they'll have different points. Some of them are a lot more complicated than others. Interfacing to the rangefinder to detect a distance away. And finally, the ambient light detector, so extending that to give you the ability to differentiate between different frequency of beacons. So the course will have several different beacons on it, running at like 500 hertz, a kilohertz, and something like that. And if you can design a system that can detect which beacon your robot's looking at, that will also be a useful sensor and part of this open source sort of bonus points. But there'll be more details in the final document posted tomorrow morning. Any questions on those announcements? Yeah.
We hinted a while back that Mark had a deadline for the first wave of 3D printed stuff.
Yeah.
Do we know anything else about that?
He was going to post on BB Learn when that was going to be, but that didn't happen, so we can ask him in the lab. I think it was going to be in the next week or two, the first wave, but
yeah, I thought it was going to be about 2 weeks from 2 weeks ago.
Yeah, that's what he had said, but I don't think has anyone submitted any 3D printed stuff by chance? One person? Did he tell you?
We haven't submitted it yet, but he also said we had a limited amount of material we had. We can't find anything for that.
Oh, really? It was supposed to be like, yeah, a cubic inch or something. So it was, there's also, if you want to test stuff, so I think the deal was, like, you could do test prints and not use that, because you don't want to print something and then say like, oh, I needed to change this. So it's just the final robot can only have so much 3D printed parts on it. But it should be in the parts list. I'll ask Mark, he's the one that does all that. And there is, the libraries have 3D printers you can use too if it might be faster. I don't think the quality is as high, the ones the libraries have, if you use them, but yeah, so we'll check with Mark, I don't know for sure. Other questions? Okay, on to the lecture. So this will hopefully be not too long, so you have a fair amount of time in the lab. I'm just going to be talking about this one sensor that you have in your parts kit, this MPU9150, and basically using the 3 different sensor devices within it, the accelerometer, the gyroscope, and the magnetometer, I think it's pronounced. But this is the final one senses the Earth's magnetic field. And again, last week we talked quickly about it. So the device itself looks like this. So you might have looked at it in your kit. You might have just looked at it in a little bag. So the only other thing you have to do is basically, these are little holes here. The first thing you'll have to do in the lab is solder these pins on it. So there's sort of a pin header you can see here, and this will let you push it into the breadboard. You could also solder wires onto the pieces you need. It's up to you. It's nice when it's on the breadboard like this. When you'll use it, you'll want it to be fairly securely mounted. You don't want it bouncing around. So the breadboard's an easy way to do that. You can tape it down if you want. But if you have other methods, it's up to you entirely. So you'll mount it in here, and it uses what's called a I2C interface. You'll see it referred to, or TWI, two-wire interface. They're the same thing. ATMEL uses this TWI name you'll see all over the place. The reason for this, I2C officially is a trademark of Philips. To avoid paying Philips money, ATMEL just gives it another name in their data sheet and calls it TWI. But it's exactly equivalent, just purely by coincidence they might say, but that's why you'll see both of those names. So the lab itself, I will sort of be giving you the code for doing the TWI interface. The ECED3901 labs have some additional information on the TWI if you want to extend this, the code a little further, which you might need to do to make most use of it. So basically for connecting it up, again, this is all in the lab handout, but I want to make sure you're sort of familiar with what's going to happen. You'll have the device, and we just have it plugged into the breadboard here. There's basically a few pins so that you can see the ground here is connecting to ground. There's a VCC pin. Make sure you connect this to the 5-volt output. So you can see this red wire here, this VCC, is going to the 5-volt. So you don't ever want to connect it to the input voltage, which is like 10 volts or something. That'll blow up the chip. So this is just 5 volts. VCC is 5 volts only. And there's also some resistors. So the resistors are what's called pull-up resistors. And they're on these I2C pins, SDA and SCL. So this is very common due to the way I2C works. You just have to have these resistors here. Around a kilo ohm will work. Normally it's like 2.2 kilo ohms, but I don't think you have that in your kit. They wire into the ATMEL processor, and this is what gives you communications to the device. And the only other thing to do, there's one pin, AD0, somewhere here, it's an addressing pin, and you just have to connect that to ground. So again, this is all in the lab manual for reference, so don't worry about writing this down right now, but you should just sort of have an idea of what you're going to be doing. So once you connect to it, it gives you what we talked about yesterday. It gives you the acceleration, or not yesterday, last time, the acceleration, the gyroscope, which is angular velocity, which is as I rotate the device, it's going to give me a reading. And that reading is solely based on how fast I rotate it, not an actual position. And it's also going to give you information on the magnetic field in the area of it. So what we want to use that for is to detect the magnetic field that is the Earth's magnetic field. And you can do this with something like a compass, which I happen to have. Somewhere, as you rotate the compass, it's also aligning itself to Earth's magnetic field. And in the same way, we want to use a robot to do that. So there we go. If you have a little compass, it has a pointer on it that'll rotate with the magnetic field. So we want to do the same thing, but with our electronic sensor. So the readings it gives you, and again, you'll see this a bit in the lab, are not just magical, the acceleration is this number with units. They just give you what are called counts. And all these counts are the output of an analog to digital converter, which is reading, there's some sensor inside the device, there's some analog sensor, whatever it is. I just have a variable resistor representing it. It goes to an analog to digital converter. So this converts some voltage, like 12 millivolts, to a number. And this number at the output is what you get. Maybe it's 1,237. Whatever the number is here. This is the output number that is read from the device. And you have to convert that number to a useful measurement. So this device has a few different ranges that you can select between. And based on the range, you can figure out what the conversion is. So very briefly, for example, the accelerometer talks about a full-scale range of plus minus 2 Gs. So the accelerometer units, by the way, are what are called Gs, G-forces. So 1 G is the force of gravity. 2 Gs would be double the force of gravity. So this is, when they talk about cars accelerating around and having so many Gs, if an airplane pulls like a 4G turn or something like that. So that's what those units are. So 1 G, 1 G is, if you want to use this, 9.8 meters per second squared, the acceleration due to gravity. 2G would be double that. So in your robot, if you just want to detect the orientation of the device, or gentle bumps, you could simply use the smallest full-scale range. The advantage of the smaller ranges, let's go here, is that it will give you a bit more precision on the reading. So what do I mean by this? If we go back, the other thing it says is, it tells you there's a 16-bit analog digital converter, and this is for the gyroscope and the accelerometer, both have this. So if we say, well, how do we convert this count to a number that's meaningful? What we say is, well, it's a 16-bit ADC. This means a 16-bit number can hold 2 to the power of 16 is sort of the range it could go from. It could go from 0 to 65535, because 0 counts as a used number, so there's 65,536 different possibilities that number could take. So you could sort of simplify that and say it could represent any number from minus 32,768, because it's signed again, to positive 32,768. Technically, it's asymmetric. It goes to 32,767 because 0 takes up 1 unit. But for what we're doing, we don't really care about that. We can just consider the scale is, it could go from minus 32,768 to positive 32,768. And if you look back at at this thing, we had these full-scale ranges. So if we have a full-scale range of plus minus 2G, what this means is that a count of 32768 is equal to 2G. Positive would be positive 2G, negative would be negative 2G. So to generate a scale factor, we can just divide the two out. And we can say, 2G divided by 32768, so this is full scale with units. And this is full scale in count. So you could simply multiply whatever the output of the sensor is by this magical scale factor to give you the acceleration in G's. And that's basically the answer. So this would change, obviously, if we chose to use a different full scale. So if we said we want full scale to be plus minus 4G, all we would do is change this to 4, and then you'd have some new number here, which would be 3 something something. So that's all the simple conversion is. And it's sort of up to you what range you would need. Again, the smallest ranges should be enough for your robot, but you might want to experiment. You might want to, if you're running into something, detect how hard you ran into it, and that's going to need above the plus minus 2G range. What else? So I already mentioned the idea of the units was these Gs, and you see this all through the spec sheet. And again, 1G, so by default, if you consider the accelerometer sitting there, if you have the X, Y, and Z axes, that's sort of a backwards view of them, you would by default expect to have the pull of gravity, so you should have 1G just sitting there in the Z axis. So when you look at the accelerometer output, you should by default see very little in X and Y and a huge amount in the Z axis. In real life, of course, one of the errors that you'll see, I meant to show you this, is there's something called cross-axis sensitivity. 150. Oops. And so cross-axis sensitivity means the device itself is not perfectly aligned within the package, so you're going to get some readings on each of the other axes. You'll also get that because you may not have it perfectly level, you just have it sitting on the table like this, but if you look at the board, it's angled up a little bit and stuff like that. But even if you were able to align it perfectly, you can look at the spec sheet, and somewhere it's going to have, if we go down, it should have, so you'll see this, come on, this cross-axis sensitivity for the different, so this is for the gyroscope, I think, but they'll all have it. And all it means is that even if there should just be entirely a reading in the z-axis, you may get, plus minus 2%. You may get up to 2% of that reading showing up in the x or y axes, or both of them. It's simply an artifact of the part. So it's something you could compensate out. For most of the stuff you're doing, it shouldn't matter. You'll be generally using them in a pretty slow fashion. So you shouldn't have to worry too much about that. The other thing, so the gyro has another set of units, and this is the angular velocity. By default, the datasheet all talks about in degrees per second. So you'll see it like that, or degrees d per s, or degrees per second. And this is actually, it's a fairly convenient unit for you. All it is saying is that, if you start with the device at some point in 1 second, how many degrees did it move? So if it's moving very slowly, in 1 second it might move 10 degrees type thing, or 40 degrees. If it's moving very, very fast, it could move 1,000 degrees in a second easily. And again, this is why we have the different scale units you can select between. So it can go up to 2,000 degrees per second. Is the fastest rotation it can detect. So you can convert that, degrees per minute or RPM or anything else. By default, I'm using the lowest, so you can sort of play with it a bit and see at what point do we, reach the limit. Oh, do I need to go up a step? So you can play with the various settings. It's all part of the software. Okay. And finally, the magnetometer units are what's known as microtesla. So you'll see them written as that. And this is simply a strength measure of the magnetic flux at some point in Earth. So this varies, oops, I don't have a slide, all over the surface of the Earth. And it talks about that in the lab notes a bit. But I think around Nova Scotia, you expect to see in the vicinity of 55 microteslas. Sort of vaguely. Around the Earth, it varies from something like 20 to 65, depending where you are on the Earth's surface. But that's the strength of the magnetic field. You'll notice the magnetometer, if we go back, it has a full scale of much larger than this. It goes up to 1,200, 1,200 microteslas. And we're only sensing, like 55. So there's a few reasons for that. One is that you might need to compensate for stronger magnetic fields nearby. If you have a motor or something, it's very easy to increase this. You might be wanting to use this sensor for some purpose besides just compassing. You may be detecting, a magnet spinning, and what's the speed that magnet is spinning or something like that. And there's no selectable. It's always the full scale range. So the other thing you can sort of figure out with this is that with the magnetometer, you notice it has a 13-bit ADC, which means it's a more limited range. So it's sort of, oops, come on. It's plus minus, 2 to the 13 over 2 is its full scale range. Previously we had 2 to the 16. So this is, I believe equivalent to plus minus 4,096. So a count of 4,096, of positive 4,096 equals whatever that was, 1,200 microteslas. So the other thing you'll notice is that a single count, so if you get a count of 1, it's somewhere around be that around 0.2 some microteslas. I don't know exactly what it is, oops. Around 0.2 something microteslas. So you don't have quite as much precision as the other sensors do relative to, you know, the strength of the Earth's magnetic field. With the accelerometer, you know, the full scale was plus minus 2G, and we're regularly sensing 1G. So the regular signal is about halfway up the scale. With the magnetometer, that's not the case. The normal signal is pretty far down, so you don't have quite as much precision. And you'll sort of see that in how noisy it'll appear when you're playing with it. All right, some quick usage notes on the accelerometer. One is that we can use the accelerometer to calculate what the robot, if it's pitching or rolling. And so how we do this is basically you're looking at the projection of the gravity vector onto, so you'll have the x, y, whichever way you want to define them, and z sensor planes, and this will mean that if you have, you know, a gravity vector pointing down, let me get a different color. So if you have some gravity vector, it's going to be a combination of readings in, you know, the x, y, if we go up, z plane. So whether we call this negative or positive, you know, depends on which way we reference it. But what this would mean is that normally you would expect this gravity vector to be perfectly perpendicular or parallel to the z-axis. So the whole measurement should be in the z-axis. As you start to tilt the robot, the sensor will see some of this gravity vector in different planes. So if you take it to the extreme limit, you know, if the board's horizontal like this, the gravity is entirely in the z-plane in the sensor. So the maximum amplitude will be, you know, the z-axis. If I rotate it like this, now the sensor, the z-axis is sticking out this way, so it's not going to sense gravity at all. It's entirely going to be in whichever this is. So this says it's the y-axis sensor here, so you can see it entirely in the y-axis. In between that, you'll see some combination of the two. And so we can calculate what those pitch and roll angles are. So one of them pitches one way and roll is the other. And it depends what orientation you claim as the front for which way is pitch and roll. But based on that, you can sort of calculate what those angles are. And this just uses the three accelerometer readings. So this was there's a full example of using the code for both pitch and roll and some simple compensation. So this was just an example pulled from that. Again, in the lab, you'll sort of see more on this, so I just want you to be familiar with the presence of it. The gyroscope is the other interesting thing. And I mentioned on Thursday, the problem with the gyroscope is the zero rate output, which is to say when you're holding the gyro entirely still, there's no rotation at all, it's just sitting on the table like that. What you'll see is you'll see some output from the thing, from the sensor. And it's saying, you know, you might get up to plus minus 20 degrees per second, which is a lot of rotation that's not actually happening. So what we want to do is we want to compensate for that rotation. So if it's constant, if it's always saying it's spinning at 20 degrees per second, we can just subtract that out and end up with a fairly useful number. So how we'll do this, and in the lab what you should see is that even over a few minutes, which is really your competition time, there's not enough, or you can make the reading stable enough to use it to detect rotation of the robot platform. And how we'll do this is we're going to measure the bias in the gyro, which is to say when it's sitting there, how much does it say it's spinning? And we're going to do this with this sort of code here that, again, you'll see this in the lab, you'll be given all of this information, is we're simply going to average out. In this case, I've chosen to average over 128 readings. So I take my gyro, I add up 128 readings in both the X, the Y, and the Z. So I sum them up, and then I just divide by 128 to give me the average. As a note, this is a sort of useful hint if you're doing coding This 128, why I'm choosing this, is dividing by multiples, sort of binary exponents, results in very efficient code. So this means dividing by 2 to the 8, things like this, 2 to the 4, any number that you can represent as a binary exponent like this ends up being that you just delete certain bits when you're doing the code, and you don't actually have to perform division at all. Division in the microcontroller is somewhat slow. Doing this is very, very fast. That's just why I've chosen 128 in this example. But once you measure the bias, you'll get a certain bias for the gyro, and I just have them measured here, stored in these variables, and then you can simply subtract them off any future gyroscope readings. The other important thing to note is that these biases might not be super constant over temperature or other things. So for example, it has this 0 rate variation over temperature, and it says, from minus 40 to 85, which is a huge temperature swing, it varies 20 degrees per second. You might want to test, how much does it vary between 20 degrees and 30 degrees. The easy way around this is, so if you have this type of code, when you first turn on your robot, you can just perform this code every time it turns on, and it'll figure out what's the bias for the gyro, and you might want to reduce this delay to reduce how long it takes. What's the bias for the gyro, and just apply it. In that case, you don't care at all about temperature variation because you've just detected it for whatever the operating temperature is, assuming the operating temperature stays constant over the course of your code resetting. The only caveat, if you want to do this, is of course, if you accidentally touch your robot while it's doing this, it's going to get completely wrong readings. So that would be very bad. Alternatively, you could do this and figure out what these values are. So you could just say, I'm going to subtract minus whatever this bias is, 121, maybe this one's 32, and this one's 48. And you could just put these into your robot, and that way, whenever it turns on, it has them pre-programmed. You don't have to do this initialization, and you don't have the concern that if you move your robot during this initialization, it'll get incorrect biases. The downside of this is that it might be sensitive to temperature, so that's something to sort of investigate a bit. In the lab, we'll just do this first part, and then you can print the biases to see them. The other thing that's interesting is, of course, performing the actual integration of the gyro. So as I mentioned, the gyro is only giving you the angular velocity. So all it's telling you is that, if you start here, in 1 second, you would move, 15 degrees or something like that. It doesn't tell you where you are. What you probably care about is if I know I'm starting facing some direction, after 30 seconds, of driving around, what's the current direction I'm facing? I can use that, reference that to a map to figure out what direction I might be facing, or if I see a light on the course map, I can say, there's this light, I know where it is. I can rotate 180 degrees and drive the other direction. So to solve this problem, we use integration, and really all it is adding up a whole bunch of these readings. So you can say, you could ask the gyroscope, what's my current speed I'm rotating at? And 1 second later, ask it again. And if you added up each of those, you would have said, well, in 1 second, I moved the 15 degrees that the angular velocity said I was moving, and just keep doing that. Of course, that's not super accurate because your speed will vary within that 1 second period, so you want to reduce the delta t, the time interval that you're integrating between. So this example code here does that to some degree, and there's a few caveats we talk about in the lab, but basically we read the accelerometer, or the gyroscope, sorry. We read the other ones, we don't need them because you're going to use them elsewhere. It's just left in there. So you get X, Y, and Z gyro readings. And we have this accumulation register, this ACC, and all we're doing is throughout the whole code, we're continuously adding to this register. And you can see at the beginning, we cleared it to 0. So we start at 0, and we just keep adding whatever the angular velocity is. To convert this back to degrees, we just use the equation here, and there's two aspects to this. So the first aspect is what I talked about earlier. This is the scale factor. And you can see it's the 250 degrees per second divided by the 32768. So this is, again, assuming I'm using the 250 degree per second full scale. This does the conversion. And the other thing here is the time step. And that's how often through I'm actually reading the sensor. Now the error in this code is, you can see I have this delay here that says we're reading the sensor or we're delaying the code for every 200 milliseconds. The actual delta T is slightly different because it takes time to print these readings to the screen. It takes time to actually read the gyro and stuff like this. So if you want to make this more accurate, what you should be doing is figuring out how long it takes to go through the entire loop. And the easiest way to do that is just to, set a port pin to trigger at some point and use an oscilloscope to measure this time frame. Alternatively, you can use the timer to give you a very constant interrupt time to allow you to integrate this, to measure the gyro at a known perfect time and not have to worry about that at all. But generally the code itself will give you the approximate answer as is, and then you'll have to do some improvements to it to fix that scale factor, or to fix the delta T, and you can play with the different gyroscope ranges. Two notes about this code that could trip you up. When I'm using printf here, so if you've done C, you'll know that printf has a floating point version, and right here I'm using the integer version. By default on the AVR, and you can change this, it doesn't include the printf statement that works with floating point. You need to link in a different version of, and they do this just to save code space. It takes a fair amount of code space to print the floating point numbers. So by default, they disable that. In this case, I'm using the default version, so I can only print in integers. So I have to do this math in floating point. So you'll see that I'm casting certain things to floats, like the variables, and then I'm using this 0.2, 250, 0.0. So I use this 250.0 to force to be a float. So the compiler is just a convenient method. Once it's calculated that angle, and that angle will be between 0 degrees, 1 degrees, 2 degrees, 3 degrees, etc. I just print it as an integer, so it throws away all the decimal parts of it. If you want, you can instead print a floating point, and in ATMel Studio you can see where you can adjust the type of printf to include the floating point library, and I can show you that if you want to do that. The other thing is there's this option that you could overflow your variables. And what this is that, where is this? Okay. At the top, I have these accumulation variables are 32 bits. If you change them to 16-bit, and you'll test this in the lab, a 16-bit variable can only hold, if it's plus minus, that 2 to the, well, really plus minus 2 to the 15 because it's signed, which is equal to plus minus 32768, as we said, or almost, plus 32767, close enough. The problem is that this gyro reading, when we looked at it in the previous class, the numbers are something like, you could get up to 4,000 counts if you're rotating it, and it doesn't take long if you're adding this 4,000 up every 200 milliseconds to actually exceed this 32,768. This is what happens when we get what's called overflow. The variable can no longer represent the number. The number that we need to represent is something like 55,000 plus 55,000. It can't do it, so it just loops around, and you end up with overflow. And you'll see you'll start rotating the device, and it'll be counting up correctly, and then it'll just skip down to the wrong count. So to avoid that, I use a much larger size variable. So this 32-bit variable can hold plus minus 2 to the 31, which I don't remember offhand. It's like 4 billion, somewhere around that. So it's a much larger number. You shouldn't run into this problem as quickly. Of course, if you leave this code running for a long time, it could still count up that high. So you have to consider at what point might it overflow. All right, so the final part is talking about the magnetometer. This is what's doing the magnetic field sensing. And again, you'll play with this in the lab. I have some of the equations on this slide to talk about some of the more advanced features. I had a paper sort of tutorial written on using it, and I'll try to post that on BBLearn or on my website or something. It'll be on BBLearn for sure when I post the slides, but if you want more details, that's a good spot to go. All the figures and stuff come from that paper. So there's a few things that you should know about when we're talking about the magnetic field sensor. The first is this idea of what is the North Pole. So when you look at a map, it's almost always showing you true north, which is where the North Pole is. So North Pole. What a compass, by comparison, shows you is what's called magnetic north, which is where the Earth's magnetic field claims the North Pole is. So if you look, whatever a compass says points north, wherever that is, it's like that way, supposedly. It will be off from the actual true north if you looked at a map. And this is because the Earth's pole actually moves around a bit in time, or the magnetic North Pole. The true north is defined geographically, on a map. This is what the North Pole is. The magnetic north will actually wander a tiny bit, and it's basically never been aligned, as far as I know, with the North Pole itself, or in recent history. The result of this is that depending where you are in the world, if you look at a compass, so we're here in Nova Scotia, if you look at a compass, there's going to be some error, so it's around like minus, 20, 19, 18, something like that, degrees off. So when you look at a compass, the true north and magnetic north are not actually aligned. So when I say degrees, just for reference, what this means is that, my compass is going to be pointing somewhere, and there's going to be an error between what the actual magnetic north is and what true north is by whatever that declination is, so 19 degrees in this case. So if you're using this, you can't just compensate if you want to find true north. If you're using this for your robot, you probably don't care about that. You just care about everything relative, how far have they rotated. So when we're using a compass, all the compass is doing is we have the magnetic field vector, and this is, again, the magnetic field vector is, the magnetic field lines coming out of the Earth, and the compass simply aligns with this. So if we have a compass, the compass needle just aligns with this vector. And that's what tells us north. For the electronic system, the little sensor you have, instead what it's doing is it's actually reading the magnitude in the X and Y planes of this magnetic field vector. So nothing aligns with it, it just says what is the amount of the component in both the X and the Y dimensions. So you don't, all you get is the readings in red. You don't get this black line here. You just get the mag X and mag Y. We can convert that pretty easily. What we care about is what is this angle alpha here. This angle alpha is what we're claiming is the difference between the north, the Earth's magnetic field, and what our sensor, where our sensor is pointing, or is related to it. So to do this, you can pretty easily see that, if you did tan of alpha, would give you, what would that be, y over x, opposite over adjacent. So you could do the arctan of that to give you the alpha variable. And we'll see this in the code. The only other sort of caveat here is that when we look at a compass reading, it goes from 0 to 360 degrees. This is sort of commonly how it goes. When we look at that, the arctan component, the problem is that if we look at, say the magnetic field vector is here, what's going to happen is that we'll have a certain amount of X and Y components, so we'll be given those X and Y components. But when we find the angle, we're going to get this angle alpha in here, and it's just going to be the angle, this angle here. This angle between the negative x-axis and that magnetic field component. That's not what we would normally call the compass heading. We'd normally call the compass heading this angle here. This angle being from, you know, whatever we're defining as the reference north, or whatever we want to define as our reference. So it could be another axis to the magnetic field line from the Earth to give us the north reference. All this means, you can pretty easily see there's basically 4 possible solutions to your problem. It could, you know, your field could be in this plane, could be in this plane, or it could be in this plane. Depending which plane it's in, there may be a fixed compensation you have to perform, which is simply, you know, adding whatever the 270 degrees, or it depends where your reference is. You know, if we wanted to get back to compared to this reference, we could just add 270 degrees. If we wanted to get back to this reference, we could add 90 degrees and then subtract 360 to get this. There's some more details in that associated paper, but you should be aware of this idea that the output of that tan function is not going to give you a final heading. It's only going to give you the answer within one of these quadrants. So yeah, so to solve it, I forgot I put this in the slide. So this is some examples of what it's showing you. So it's saying, you know, if the value of the x is below 0, it means that we're in, so if x is below 0, it means we're in this half. So we can perform some fixed offset to account for being in those 2 quadrants. Or if x is greater than 0 and y is less than 0, it means we're in this quadrant here. So again, we may have to form some flip of the angle. You can go through and figure out for each of the possibilities to see what that is. All right, so the other important thing to mention that you'll see a little bit of this in the lab. The magnetic field sensor, all it's doing is sensing magnetic field. It doesn't care whether it's the Earth, whether it's because there's a motor nearby, whether you have a magnet in your pocket for some reason that you're using with it. It's just giving you magnetic field sensor. So there's 2 forms of errors you'll see. One of them is what's called a hard error, a hard iron error. And what this is doing is this is a constant offset of the magnetic field sensor. So this rotation, the circle that you see here is supposed to be a perfect circle centered around 0. That would be like a nice magnetic field sensor as we rotate the device. It should be circled around 0. It's not in the green circle here because there's a small magnet nearby or something, and that magnet is just adding a constant offset. So if you had a magnet, it would add a constant offset that's always going to add to the sensor, and so you just get this constant offset here. So that's one thing you might have to fix, and that's what we'll see in the lab. Because there's also errors in the magnetic sensor itself causing this constant offset. The other thing you'll see that's a tiny bit trickier is what's called this soft iron error. And what you can see here is that rather than being a nice circle, we've ended up with an ellipse. And this is the case where if you had, you have your magnetic field sensor and you have a big piece of metal running underneath it or something, this will also contribute to errors, but it deforms the readings because it interacts with Earth's magnetic field. It's not providing a constant offset. So if I had my board and I just had a magnet here, there's always going to be, in this, say this is the Y direction it says, there's always going to be 5 microteslas in the Y direction. And that's just going to pull it over 5. And it's just going to still have the same circle, but pulled over. If I put a piece of metal under it, it doesn't have a constant. The metal itself doesn't have a magnetic field. What's going to happen is as I rotate this, if I rotate this and the field's going through it, the Earth's magnetic field will interact with that metal and give us this funny ellipsoid reading because depending on how it's oriented, it may or may not interact with the metal. So we call that the soft iron error. And in the same way, so in the gyroscope I talked about there being a bias, that being if it just sits here, it's going to say there's some, movement when there isn't. For the magnetic field sensor, what we have is, even if there is no other magnetic field around it, the sensor itself has some error. It has some bias in, X, Y, and Z direction. And you absolutely have to compensate for that to use it. So what you'll do in the lab is you'll plot if you read the sensor data, so what this is the X, Y, and Z sensor data, and you'll print this. The only critical thing is that to generate this data, I have to take my board and rotate it basically in every axis. So I just sort of rotate it all over the place. The idea being to, you can think of sweeping the Earth's magnetic field vector, and I'm trying to sweep it through every sort of possible orientation of the device. It's a little tricky because you don't want the boards to disconnect, or you'll lose the data dumping. So you sort of have to hold it up at one side. If you hold it on this side, you might reset it. So there's a lot of finicky bits to this, unfortunately. And it's plugged in, of course. Don't be a fool. And you'll just sort of rotate it around. Once you do that, you get the X, Y, and Z data, and you can plot it. You can plot it in MATLAB or something. I'm using this online web service, plot.le. We need a 3D scatter plot, which, as far as I know, Accel doesn't do, so that's why I'm using something else. Again, if you have MATLAB, you can do it in that. I don't know if all those computers have it. But what you should end up with is, in theory, if things are working, this perfect sphere. And the sphere is based solely on me rotating. Let's see, can we zoom in? Oh crap, too far in. Okay, there we go. So the sphere is based solely on the points that I rotated it, so it might be kind of hard to see because of the wireframe nature, but you should be able to see there's sort of a nice sphere there. And it's not centered though, so this is the raw sensor readings before I've done anything. And if I look at the graph, maybe it's easier here. If you look at the graph, you can see that the center is, somewhere here, which in the Y appears to be around 50, and the Z minus 100 something, and the X is maybe minus, I don't know. It's hard to see in the X in this figure. But what we want to do is we want to take that sphere and just shift it around the origin. So rather than sort of trying to figure out that the points from this figure, one solution is actually fit a sphere to your data points, find the center of the sphere, and that's your offset. The second solution that's a tiny bit easier is to put some code on your device. And all we're going to do is we're going to do this same thing. We rotate it around all over the place, and we're simply trying to detect what is the maximum and minimum point in each axis, in the x-axis, the y-axis, and the z-axis. Because what this will give us is this gives us, the limits of here and here, the limits of here and here, and the same thing in, well, in this case, the x. And if we average between each of those limits, that's going to give us the center of our sphere. And simply, you'll just keep rotating the device, and it's continuously calculating what it thinks the center of that sphere is based on the maximum and minimum limits it's seen. Once that stops moving, it basically means you've probably found the actual center. And in this case, we simply subtract whatever that offset is off our reading. So remember, because we're subtracting, watch the signs. This is really minus 14. The lab has a better example of this. This is minus plus 53, and this is minus 124. You can just leave them like this. That's the best thing to do. The compiler will deal with the sign issues. This bias will be highly dependent on how your system's mounted and what's around it. So in your robot, you'll want to mount this down. If you want to use this, you'll have to mount it on your metal plate, have your motors there, possibly turn them on. and perform this rotation. And what you might have to do is set up your system such that it turns the motors off when it does the compassing, because the motors being on will generate a strong field which will interact with this. And you'll get different numbers. So if you do this once it's mounted, you'll get different numbers, and you can just hard code them in. Your code is sort of the easiest thing to do. With the gyro, it was really easy to do this, real time before we use the robot. With the magnetic field sensor, it's not, since we need to do this complicated rotational test to generate all the data points. So you'll want to do this offline, so to speak, which is to say just manually figure out what they are and apply them to your system. As an example, we can do the same test. So I just taped this motor right beside the sensor. And if I do that same test, what I should see is I should see some ellipsoid like this. And let's show you, I forgot to show you two, where's my data? So once you do the bias compensation, if you want to check you've done it correctly, the best thing to do is you can do a scatter plot again. And what we should see is this should be a sphere centered around 0. And this screen is hard to see everything. Let's see. So you can see it looks like it's centered around 0, basically. And I haven't done as many points. You can see my sphere isn't very good because I sort of I'm like missing half of it. So that's why it's important to try to rotate it around all axes. But it does look like a centered sphere, more or less. So that worked. So the final thing. So I've now taken that same, so I've already done the bias compensation. I'm now adding a motor nearby. So the motor has a combination of errors. But what we'll see is that our data will not look so nice. So it looks sort of ellipsoid. You can see it on this angle really well. And not only is it ellipsoid, but it again has a really strong bias. So the magnets in the motor has given us the hard iron error, which has shifted the whole thing. And all of the metal around the motor casing has given us this soft iron error. So you can see again, it shifted way over. So we have to recalibrate this. And there's actually a separate method to compensate for the soft iron, which we won't do in the lab, but it's something that you might want to investigate. So let's look at that quickly. All right, sorry, this didn't end up being as short as I thought. So the compensation, we've determined the hard iron, which is just that offset error. The second part of it is the combined soft iron or scale factor error. All this is, so this little equation here is in vector notation, and it just means that for each of the x, y, and z, there's a combination, so you have h raw x, h raw y, h raw z, and all I'm doing is I'm subtracting, this offset y, x, y, z. And this offset, this b, is just whatever was needed to center the sphere. The other side of it, the z matrix, is just applying some sort of multiplication scale factor to each of the x, y, and z's. And the easiest way to figure out what that is, if you want sort of a really straightforward method, the proper method would be to look back at these and to fit a ellipsoid to the data to figure out what the scale factors are. But a sort of easy way is to determine, if the x range is, to figure out a scale factor to cause all the x, y, and z to appear to be roughly the same range. So here you could say, well, there's obviously a bias because it spans from -50 to 55, and it should span positive and negative symmetrically. And there's a range also of about 105. In this guy, there's a different range here of about 100 and No, 75? And the final one, there's some other smaller range, whatever that subtraction is there. And we could just multiply each of these to end up with, you know, we want to scale it such that it spans from minus 100 to positive 100. So you could say that was the objective. And all this means is a combination of the shift as well as the multiplication by a fixed scale factor. And that will help with your soft iron compensation. The final thing to consider is that you can test this in your lab. Everything we've talked about so far assumes that this unit is perfectly straight. As we pitch it or yaw it, rotate it, what's going to happen is the angle that the magnetic field cuts through the sensor will sort of contribute to further error. And you can really basically think of that, you know, up here on the Earth, the magnetic field is actually entering at a fairly strong angle. And if we were to tilt our sensor such that the magnetic field is parallel to it now, what's going to happen is there'll be no reading at all in one of the axes, in the y-axis, for example, because, or it would be entirely in that. So if you pitched it the other way, at 90 degrees, you get no reading in the y-axis at all because it's perpendicular to the y-axis, for example. So what you need is you need to actually take into consideration the x, y, and z axes of the magnetometer. To do this, we need to perform what's known as tilt compensation of it. And very briefly again, there's more details in the document I reference. But very briefly, when you're doing this, you have to be concerned about navigational frames. And navigational frames are sort of how we compare what the sensor sees to what's happening in the world. So what the sensor sees, so if we look at our sensor, it's always going to say, you know, X is always forward, Y is always to one direction. And it's even printed on the circuit board. You'll see a little thing that says X, Y, and Z is up and down. The other frame is, you know, the world frame, or what's really happening in the world. So if north is this way, and I have my sensor aligned like that, it would say, you know, positive Y, reading from the circuit board, is aligned with north. What's going to happen is I can rotate this device, and Y will no longer, Y is now, or let's face it this way, Y is this way, north is this way. There's some angle between the navigational frames. So what we end up having to do is have a method of converting between all these frames, which is to say that in our compass, we talked about declination. So I have the magnetic field vector, say, is going this way. There's a certain amount of declination because I could define, if I define north to be X, I already said, you know, there's a difference between true north and magnetic north. So there's 17 degrees of off. There's also this inclination. This inclination is actually the angle that it's entering the Earth at. And this, you know, in Halifax we're somewhat far north, so it becomes a fair, you know, moderate amount. I think here this is accurate for Halifax, is 56 degrees, so the magnetic field vector is actually entering the Earth at quite a steep angle. So if we ask ourselves, well, what projection, you know, this magnetic field vector that's a 3D vector, what is the magnitude measured on, you know, a magnetometer that's facing exactly true north, true east, and straight down into the Earth? What would that components all be? And we can just use trigonometry to figure out what these components are. And here we have the magnitude of the entire field is BH, so this is what, you know, is like 55-ish microteslas, whatever it is here in Halifax, so that's the magnitude of that. And if we know each of those angles, what we end up with is the magnitude of the readings that we would get from this sensor associated with the north axis, the east axis, and the down. And again, this is for a specific declination, which we know in Halifax, and inclination, again, which we know. And once again, assuming our sensor is facing this exact frame, assuming X is facing north, Y is facing east, and the Z axis is facing down. What we might have to do, though, in real life, is when we do these readings are, at this point I'm saying it's perfectly aligned. The x-axis is facing north, the y-axis is facing east, but it's not always going to be the case. It might be that it pitches up a tiny bit. In that case, we actually have to convert, so we have to say we measured in a different reference. We no longer are perfectly facing, down. We're facing at some angle to down. Or we rotate it slightly. The x-axis is no longer facing north. And this is the real problem we have in real life. This is rotated or in some fashion. So this is where we get into what's called frame conversions, navigational frame conversions. And this is basically that the car in this case is rotating. So what it's calling X, if the car were to rotate, what it calls X, Y, and Z is no longer perfectly aligned with the northeast and down reference, or whatever reference we're using. So we can define some of these angles around the difference between the frames. So for example, if we have this device and we're yawing, it says, what is it called? Yaw occurs around the down axis. So if down is facing this way, if I rotate this slightly, it has a slight yaw. I can do stuff like if it pitches, occurs around the north axis, so the north axis is this way. If I pitch it, I'm pitching left and right like that. Or if I roll it, and the roll is occurring around the east axis, which would be sort of this type of movement. So there's a certain amount of either yaw or pitch is what we'll really care about. We'll see. And we can measure, the critical thing is we can measure the yaw and pitch if we go back to the accelerometer. So this is where we get into using all of the sensors. So if we go all the way back here to the accelerometer, we can calculate pitch and roll based on the acceleration vectors. And we can use that to perform this frame conversion. And what we'll really care about is to convert from the sensor frame, so from readings that the sensor has given us. So this X sensor, Y sensor, Z sensor, or the magnetic field observed by the sensor itself. And we can say the sensor has a certain amount of pitch and roll compared to that northeast down. So again, we're saying it's pitching up a certain amount compared to whatever the Earth's magnetic field vector is going this way, or not magnetic field, the acceleration vector going straight down. This device is pitched up slightly. Because of that, the measurements of the magnetic field sensor are going to be thrown off. We have to convert them from the sensor frame of reference to the northeast down frame, and we can do it with these matrices. Have a special name, DCM, directional cosine matrix, I believe is what it's called. But it doesn't really matter. What you care about is that it gives you this this end result, and it's simply a matrix multiplication where this is x, y, z. So you can see it's x sensor cosine of the, what did I define that as? The roll plus y sensor sine of the pitch, sine of the roll, plus z sensor cosine of the pitch, sine of the roll. There's no yaw in this because we assume we're sort of defining the sensor board. It's the yaw axis is what we're trying to figure out because that's the difference between the north and the sensor board's whatever y axis, whatever we're defining. So because of this, there is no yaw. We've removed the yaw from all of these equations here, which back here we basically set the yaw to 0 and eliminate any that we can. so if you want to use the actual compass sensor, and this part isn't part of the lab, this is sort of the extra part that you might need. Basically what you'll have to do is figure out what these pitch and roll angles are and insert them into this equation to give you the X northeast down and Y northeast down. Once you have those, you can pretty easily, do I have the compassing? Apply the compassing equation, which is in your lab. I don't remember if it's in, oh yeah, here it is. So then you can apply this to give you a perfect heading with tilt compensation. If you're lazy, you can just use the X and Y from the sensor itself. So if you set Y sensor, and an X northeast down equals X sensor. So this will work. The problem is that if your robot tilts up and down at all, your heading will be thrown very far out. So it's sort of up to you. You could use entirely the compass if you want, rather than the magnetic sensor. Or you can use the magnetic sensor, which has very good long-term stability, or even tilt compensated. So there's lots of options for you. But that's sort of the very brief overview of the sensor types. And then just to check, there's no more. Nope. So with that, I guess we'll go to the lab. Are there any questions before I begin that? Sorry this went a little longer. I thought it would be a short lecture.
I have one
Quite the
question
opposite,
about how you were powering the breakout board. It says in the data sheet that the maximum voltage that we should use for normal operation is something like 3.4 volts.
Yeah, so this little breakout board actually has a regulator on it.
Okay.
I should have mentioned. So I don't even know if there's schematics for the breakout board fully. It's sort of from some random web store. It was cheap, that's why they got it. But yeah, it has a very small, right here, there's a voltage regulator. So you can use this breakout board up to 5 volts, no issue.
Right. And then the inputs, are those okay with 5 volts as well?
Yeah, there's supposed to be a converter on it. I don't know if they just have a diode protection, but in theory, they told us it works all with 5 volts. It seems to work when I've tested it, whether or not that's breaking it, but it's similar. They're not quite the same, but you can see the, I think the SparkFun one is very similar to the one we have. So this guy, no, this is not the same one, because this one doesn't have a voltage regulator at all. But yeah, it's supposed to have a 5 volt input tolerance. I've never fully tested that, but that's what we're going with in theory. So.
Well, you got output, so.
Yeah. Any other questions? All right, that's it.